In this problem, we're trying to find the internal loads at point D. So we want to find, since we're in 2 dimensions, what we're going to call PD, the internal normal force, VD, the internal shear force, and MD, the internal bending moment. As is typical, we're going to try to find the external supports first. This is statically determinant, so we're going to be able to do that. So solve the external problem first, then we're going to jump in and see what's happening internally at point D. So we're going to start with our free body diagram. And the first one is going to be the external picture. So picture 1 is going to be the wooden beam separated from its supports. So A through B through the end here. And D is not going to even come in play in this picture. So first, the external loads happening to this object that we're keeping. We're going to copy exactly this 900 Newton meter couple at the end. And applied is also this distributed load at 600 newtons per meter of intensity over the 3 meters of the beam. So it's a rectangular or uniformly distributed load, 600 newtons per meter, times the 3 meters it's acting on this beam is going to give us 1800 newtons is the equivalent load. And it's going to act at the center of the beam because, again, it's a rectangular load, so at half of its distance, so 1.5 meters from each side is where that load is located, the equivalent load from the distributed load. So for this external picture, I am taking the entire 3 meters times the 600 newtons per meter to see the equivalent loading. Now we need to look at the supports. At B, we have a 2-force member. B is a pin, C is a pin, and member BC has no other forces acting on it along its span. So member BC is a 2-force member, so I will use it as such. So I will say, assuming tension, the force in member BC. And we're given that it acts along this 3, 4, 5 triangle as its direction. And at A, we are going to have, it's a pin, so an AX and an AY. This is the complete external free body diagram, and if we look at the unknowns, it's the supports at A, AX, and AY, and the 2-force member, the force in it, FBC. So we can write some equations and start to get numbers for those 3 unknowns in this statically determinant external free body diagram. So I'll start by taking the moments around point A so that I can get some numbers right away, and this is in picture 1. So doing that, I'll work left to right. AX, AY don't appear. I will have then a clockwise, so negative 1800 times its moment arm, 1.5 meters from point A, minus the vertical component of FBC is 4/5 FBC, and it's going to be located 2 meters away from point A. So vertical component 4/5 FBC times 2, and again that is clockwise negative. And then I have the couple at the end, also clockwise, so a negative 900 Newton meters. Keep in mind, the couple just is already a moment. I don't need to multiply it by a distance. It's negative 900 no matter where it would be located when I take the moment around that point A. So by design, I did that first because FBC will be the only thing I do not know, but I'll write out my next equation while I'm here. Sum of forces in the x direction. In picture 1, I have all of AX plus 3/5 FBC. That is the horizontal component of that 2-force member. And once I know FBC from equation 1, I can find AX. And equation 3, sum of forces in the y. In my external free body diagram picture, AY minus 1800 down, minus 4/5 FBC. Looking at my 3 equations so far, there's 3 unknowns. I am going to take the time now to solve them. So in the order I made my equations by taking the moment around A, I can find FBC from equation number 1, and FBC is going to come out to negative 2250 newtons, and that means that the member is actually in compression. So I will put a note there, it's in compression. It won't really affect the problem, but it's good to know. Now, applying FBC into problem 2, or equation 2, AX is going to come out to be 1350 newtons. And it's positive, it agrees with my assumption of direction. And then equation 3, again using FBC, AY actually turns out to be 0 because of that couple at the end. So this was just solving the external problem, and what this will let me do is now have enough information when I go to the internal problem that I will have enough equations for my unknowns. So 3 equations for my 3 supports. So far I haven't actually found what I needed to ultimately find, those internal loads. So now I need to make a cut at D, which I will illustrate here. So I'm making a cut through D, and I can take everything to the left or the right of the cut. I'm going to choose to take everything to the left of the cut to make picture D. Right? There's just less going on there. It will include everything happening at A, but by this point I already know it. And as a note, D, I don't need a plus or a minus. There's no difference just to the left of D or just to the right in this problem because there is no point load acting on D. That's where the difference is if we're just to the left or just to the right. But this one, everything is the same, left or right of the cut. So capturing my picture here, I will have going from A to D, and zoomed in, I can see the centroid there. I have my point A, and this is going to be 1 meter in length. So what I need to pay attention to here is the external loading. I have the distributed load, but only acting from A to D. So I only have 1 meter's worth of this uniform distributed load on this section that I'm taking. So what I need to include in this section cut picture, this internal picture, is 1 meter times 600 newtons per meter is 600 newtons is the equivalent load just acting on this AD section. So I'm not taking the entire 1800. I need to base this picture D back on the original picture where I had the distributed load. What I don't want to do is say, look at my free body diagram 1 that's already simplified, make that cut and say, oh, well, to the left, there's no external force because that 1800 was in the middle. No, free body diagram 1 was already simplified. So I need to go back to the source to include just the 600 newtons of force acting in the middle of this section. So this will be in the middle of this 1 meter, so 0.5 meters from either side. So that's the external loading acting from the uniform distributed load from A to D. Now I have my support at A. I have my AX, which turned out to be 1350 newtons to the right. And AY turned out to be 0, so I'm not going to draw the AY here since it's 0. Finally, in this picture at D, where I made that cut, I can now see the internal loads that were holding the material together. Always out from the normal of my cut is my internal normal force, P, and I'll call it P sub D since the internal normal force can vary along the length of any member. So specifically at D, this will be the internal normal force. Parallel to the surface of the cut will be my internal shear force, V sub D, and then an M sub D. I chose up for V sub D. I chose counterclockwise for M sub D here. There will be, when we get into strength and materials, assumed directions for both the internal bending moment and the internal shear force. But for now, it's fine. Just I'll say up for V sub D, and I'll say counterclockwise for M sub D. But the P sub D must be out from the surface of the cut. That is now my complete free body diagram for that section cut at D. And it's a 2D rigid body, so I can get three equations now from this figure. And these are typically going to be pretty straightforward. So in picture D, if I sum forces in the x direction, I am going to get 0 because it's in static equilibrium. And looking at the picture, that's 1350 plus P sub D. If I sum forces in the y, in picture D, I will get minus 600 from the distributed load, the simplified equivalent load from the distributed load, plus V sub D. And 6. If I take the moments about the centroid of that cut surface, so this point is always representing the centroid, so taking the moments about the centroid at D, in picture D, it's going to sum to 0. I will have, well, the internal bending moment m sub d, and I assumed it's positive. I assumed it was counterclockwise. P sub d acts through the centroid, so it does not contribute to the moment. V sub d acts through the centroid, so it does not contribute. So I will have plus 600 newtons times 0.5 meters from the equivalent load from the distributed load. And the 1350 newtons also acting through the centroid, so it does not contribute to the moment either. 4, 5, and 6 now are going to give me my internal loadings at point D, and they're going to be pretty easy to solve. Equation 4, the only unknown is P sub D, so I can solve for that, and that turns out to be a negative 1350 newtons. Internal normal forces, because we're always drawing them assuming tension, always for an internal normal force, negative will mean it's in compression at that point, positive will mean it's in tension at that point. So at point D, we have a compressive internal normal force of 1350 newtons. Equation 5, the V sub D, that turns out to be a positive 600 newtons. Now for shear forces, we do not make any sort of inference about how the sign affects tension or compression. Tension compression does not apply to shear forces, only normal forces. So 600 newtons, it's really just telling us that the direction agrees with our assumption. And equation 6, m sub d, comes out to be negative 300. Everything's in base units here, so Newton meters. Again, the sign on the internal bending moment does not tell us anything directly now about tension or compression. It just means our assumption of the direction, in this case, was incorrect. Now later in strength and materials, these signs do make a difference because when we are looking for stresses, compression, tension is going to matter, as you'll see later in strength and materials. But here, the only inference we're making on the sign is on the internal normal force. So we found the internal loads, all three of them, from that internal cut free body diagram at D. Before we got to that point, we wanted to solve the external picture first, because if you'll see in that picture at D, that 1350 newtons from AX, it was helpful knowing that going into the internal cut, because now only 3 new unknowns were introduced, and it was a very easily solvable system. That's because we started with solving the external problem, found AX and AY, and FBC.